Yeah, so this is part 4 of 5 parts, and let me just recall what I tried to do yesterday. I tried to explain several ways of representing a topological space on a computer. I illustrated gap code for some of those representations, for the simplicial complex and for the CW complex. I did talk about simplicial sets and semi-simplicial sets, and I didn't illustrate those yesterday, so that's really what I want to do today, use some simplicial sets. But before I do that, I'd like to finish off. Philippe wasn't here yesterday, so I stopped early, and now I have to catch up on the bit that I didn't cover. So to recall then, at the end of yesterday, and what I was also trying to get across yesterday was that homotopy or discrete vector field, or whatever you want to call it, can be useful in the computer, and that's well known. In fact, when Alexander has talked about Tietze transformations, my understanding of history is that Henry Whitehead generalized the ideas of Tietze transformations when he introduced simple homotopies, which is about discrete vector fields and so on. So we are talking about similar topics. Okay, so I ended up yesterday talking about the cup product, so I won't repeat this again, but it's a product where you can take cohomology classes of degree p and q for your topological space X, and you can output a cohomology class of degree p plus q. So I won't repeat too much about that, but I do have a gap illustration that I didn't give yesterday. At the end yesterday, I mentioned that the current implementation in HAP is very poor because I do something criminal. I take a regular CW complex and I say, how do I construct a diagonal approximation? I say, well, I don't know how to do that, but using Alexander Whitney, I can read it from the Wikipedia how to do it for simplicial complexes. So using barycentric subdivision, you can always construct a simplicial complex and do that. And that's what I did. But I did say that at least in low degrees, this picture, I won't go through it again, representing a kind of a diagonal approximation of a cell, which is certainly not this is a two-dimensional cell, which is not triangular, it's hexagonal. Kind of the image looks like this. I talked about that yesterday, I won't repeat it again, but I do want to give the gap illustration that goes with this picture. So I'll do that now. And also what I should have mentioned yesterday is some of the examples yesterday involve spaces that have lots of cells. They're very big spaces. And so ideally, you should use lazy evaluation. Only calculate things if you really need to. Yeah. So some of the implementation so far in HAP has been a bit lazy in that I haven't used lazy evaluation. But in the example I'm going to give today, some of the cell complexes are going to have infinitely many cells, so that clears up the problem. You have to be lazy because you can't compute things on infinitely many cells. So lazy evaluation is what I'm going to illustrate today. But now let me go to a gap example of the low-dimensional cup product. Hope I can find it. Now I'm nervous using my fingers. I'm going to stick just for the moment to the... let me just copy completely one example into gap and then explain it as we wait for it to work. Let me do it this way. At least it works that way. So what am I doing? I'm first of all reading in 2 artificial knots that I've created. So these are synthetic knots. I've just input a sequence of points in 3-dimensional space, joined them up, and I've got two knots. And my question, who can tell me how many times one of these knots wraps around the other? Can anybody give me the the linking number, how many times does the one wrap around the other?
You want to see the projection, so it could be like.
Oh, well, have I, sorry, well,
Okay.
I just kind of keep doing this. Anyway, let me go on. That didn't work for audience participation. Okay, so now what I'm going to do is those two pictures I'm going to recreate as cubical. Now, I'm using the cubical tessellation here. So I've created a pure cubical complex inside a portion of three-dimensional space, and I'm taking the complement. So there must be 101 points in each of the knots, and so we have some approximation, which is a cubical complex, and then I take the complement, and then I simplify things using discrete vector fields and so on, and then convert it to a regular CW complex. Oh, the size of the original complex in terms of cubes, there are 250,000 cubes, and I guess each cube has so many vertices and so on, so it's a large cell complex. You contract it, work out the fundamental group, for whatever reason. But I'm going to compute the cup product from degree 1 across degree 1 to degree 2, because you can read in the Wikipedia that the cup product there, in this case, gives you the linking number. It tells you how many times one knot wraps around the other. So if I press return, I'll see how many people were right. 6. But the point there isn't so much 6, it's the speed. I mean, if you use a little bit of imagination and don't go to the Wikipedia and use the Alexander Whitney, things can work quickly. The problem is, how do you do this calculation for higher dimensional cup products? And that's something that a PhD student is thinking about as I speak, I hope.
Show us the picture again.
He doesn't believe me.
Write out the 6.
Where was it? I have to... I mean, it's how many times does one... I suppose you pick one and, oops, what have I done now? I don't know. I've made the things...
Where can you read of anything?
Well, one is kind of wrapping around the other. Well, okay, let me rephrase it then. Let's calculate the cup product on the cohomology of the complement. 6? Oh, the cup product, yeah. The cup, and how about the I hope it's 6 anyway, otherwise the Wikipedia needs... Sorry? Well,
because if they wrap one,
yeah. Well, how many? I don't know how many crossings are there. Oh gosh.
1, 2, 3, 4, 5, 6. I think it's 3.
Okay, so let me think about that. Okay, so maybe well then.
Oh no, but you also.
But the knot itself is twist. I mean. The knot is anyway. What I'm trying to get across very poorly is that cup products can tell you about linking numbers. Let me just move along. So that was an example about. And then the other thing I will just briefly show a bit of computer code, not very sophisticated. What do I mean by lazy evaluation? I talk about lists, but it's not too difficult to create infinite lists. And they are handy when implementing things in topology. So let me just illustrate an example of what I mean by lazy. So choose some function. I think I've created a function which inputs something and returns the square. And then I've created it inputs an integer, and I've created the lazy list of all the squares. So what's the fourth term in my list? it would be 16 4 squared, and the fifth term would be 5 squared. And then I could ask for things like, what's the length of the list infinity, and what's the position of 36 in the list? It's 6. It's nothing very deep, but I'm using lists which can be infinite, is the point. So you can adapt gap to use infinite lists, and then you don't have to think too much when you're programming. You can still use lists, but don't worry if they're infinite. And when you want to evaluate things in a lazy fashion, you can do it. Okay, that was the end of yesterday's lecture. Given that Philippe is here, I thought I should finish it. So, yeah.
I'm sorry.
No.
Did you explain, did you told us what elements you do the dot product to obtain
No, I didn't. Well, I take the so that's a very good question. I took the generators, and you have a choice of the generators of the cohomology. So I didn't tell you that the cohomology there the first cohomology. Yeah, I took it on generators. Yeah. It's the first. I took it on the two generators in dimension 1, and then you get something in dimension 2, which is 6 times the generator. And I didn't know I suppressed that. I just wanted to get the 6 across. I'm thinking now it wasn't a great example. But yeah, no, that's it. So let me just continue. A little bit more before on this. So that was the gap session. I will mention, maybe I won't run through this example, but I will mention that there's something called the linking form. So the linking form is a form which inputs 2 elements of the torsion part of the first homology of your space. So in the examples that I would talk about, the first homology would be finite. So it inputs 2 elements in the first homology, and it outputs a number in the rationals modulo the integers. That's what it is. And how do you construct it?
You have different numbers of t in there. Is that conventional, or should that be a t in front of it?
There should be a t everywhere. It's a tau, but a th, a tau, but different numbers of t. Oh, sorry, sorry, I've forgotten the one. There should be I mean the finite part of the first homology. I've forgotten one tau. Tau. So yes, and there's a typo there. I missed one tau. So it's. No, it's so what actually goes on here? You use Poincaré. So I should say that this is. Let me just be a bit more precise. This is defined for an oriented 3-manifold X. So in general, it's not defined. So an oriented 3-manifold has the property that it's third closed 3-manifold, no boundary. So that has the property that the third homology will be infinite cyclic. And then you have Poincaré duality. Closed compact. Closed compact manifold. With top homology Z. Yeah. And then Poincaré duality. What does that say? That says something like the cohomology is related in some way to the homology. I probably got this wrong. N, or I suppose N is 3 here. And so this can be implemented. And you have to be a little bit careful because, you know, it's not an orientable manifold, it's an oriented. So an orientation on a manifold is a choice of generator for Z. And you do have to worry about whether you choose +1 or -1. It doesn't matter which you choose, but you have to choose one and stick with it. So it's an oriented manifold. You can implement this. So I think that's being used H2. So if I take k equal to 2, H2, I somehow identify the second cohomology you can identify with the first homology. And so that's being used in the first map, and then the second.
And W equals X or X?
X, so that's another typo. Yeah. Sorry. X is W is X. Yeah. Sorry.
And this is true without tensoring with Q? Or
Yeah. No, this is true. This is true. Full stop. Yeah. That's true. Full stop. And then you have the Bochstein. So I won't write it down, but there's an exact sequence of coefficients, and you get something called a Bochstein or a Bochstein homomorphism, which brings us down to the finite part of the first homology of X cross the finite part of the first cohomology of X with coefficients in Q mod Z. If you write down the box, I won't write it down, but the Bochstein, you get that, and then you evaluate and you get this number. So that can be, I think I'll skip the example. In the code up on the web page, you can try it if you're interested. The code illustrates how this can be used as a Homotopian variant of a manifold. So what you can do is you can take a manifold, for example, a lens space like we were talking about yesterday, X, and for all elements. Now, I guess there are two choices of orientation, and as we want a non-oriented Homotopian variant, choose both. So X plus and X minus means the same manifold, but with different orientations. And then you iterate over all elements in the first homology, take the linking form, and you'll end up with a fraction between 0 and 1. Take the union, and this set is a Homotopian variant, and you can use that, for example, in GAP to distinguish between lens spaces. And in fact, it distinguishes perfectly the homotopy type of lens spaces, because that is actually how Whitehead classified lens spaces up to homotopy originally. So I won't run through the example, but it's there for those that want to do it. So I won't do that. But what I found interesting, and maybe I can say a little bit about this, you can also use the linking form to distinguish between the homeomorphism type of compact, closed, oriented manifolds. I think I got all the words there. You know, the three manifolds. So,
will you give an example of a non-trivial evaluation to Q mod Z?
well, I can run the example. I could. Well, do you want me to run the gap? I'll run the gap.
No, maybe you can have one without. Just to get the intuition going. So anything that goes to, say, 1/2. I think our group or something, there's in the brow group, what's a non-trivial map going to 1/2? Quaternions or?
I think I won't run. I can run the gap, but it just takes a couple of. I don't have an example in my head. But you can also use this to determine the or to distinguisch between homeomorphism types. So there's a paper. Reidemeister and Moyes first determined lens spaces up to homeomorphism back in ancient history, and then Brodie subsequently, without using the Hauptvermutung, gave another proof, and his proof goes as follows. You might have a fundamental group of a space. In fact, your space might actually be a lens space. So its fundamental group, if you use theory or gap, would be cyclic of order P from. Now, to me, this is I've already just thought of the cyclic group of order P as not much to say about it, but the elements are actually different. The generators are different. So what you can do is you can take a loop representing a generator in the space. And then you can thicken it and take the complement, and then you're in the business of taking complements of knots in, say, lens spaces. I won't go into the details. It's implemented in HAP, and you can use this to distinguish between certain homeomorphism types, and it turns out that it is actually sufficient to reproduce the classification, the distinction for lens spaces. Yeah, so the reason I wanted to mention that was, I think, rather than the details of that, this kind of elementary picture here I find interesting. So when this was first implemented, wrong answers were coming out. And of course, you mustn't simplify things up to homotopy if you're trying to give a homeomorphism classification, because, yeah. So you actually have to simplify things up to homeomorphism. So you have maybe a CW structure on a manifold with lots of cells, and you want to reduce the number of cells, but you need to think a little bit, and it's a bit more costly than simplifying up to homotopy. But you can do this kind of thing. You can remove cells. You can remove this cell without changing this particular space up the homeomorphism type. And you can do kind of a subset of a discrete vector field to obtain a more subtle reduction, which is a homeomorphism invariant. Yeah, so that's involved in there. Okay, that's the end of yesterday's lecture. Are there any questions on that? Got rushed. Then I'm going to justify having spoken very briefly about simplicial sets. So I'm now going to talk about simplicial sets on the computer, and I'm a little bit embarrassed talking in Grenoble, because Grenoble is the home of Kenzo, which is, I suppose, the ultimate software for calculating with simplicial sets on a computer. But some of the ideas from Kenzo are re-implemented in GAP. Okay. So suppose that you have a small category G. In fact, for me, a category with one object is a group. So I'm just going to think of G as a group. I'm going to restrict categories to categories with one object. So I think of a category with one object as a monoid, and most of the time it's actually going to be a group. Yeah. So oh yeah, I don't know what's a set and what's not a set. It has to be the object. Yeah, I think the elements have to be sets, and so that's whatever a set is, and so on. It's a yeah. I mean, it's these things are going to be very countable and yeah. So.
By small, he means literally the object has to be sets.
Yeah, sets, and this yeah. No, but
well, groups are sets, but the class of and like the set of the class of sets is not a set. But if you take, for example, all finite sets or all finite groups, that's also not a set. But you could say it's essentially small because you can find an isomorphism for each one. Small finite sets are just identified by the cardinality.
But I mean, they're going to be finite here. So I can. Let me just say finite, then finite categories. Ooh, yeah, okay. So which is or countable anyway, at least, So the nerve of a small or of a category or of a monoid G is the simplicial set. Where, if you recall what a simplicial set is, it's a sequence of sets, and in degree 0, there's going to be one vertex, if you like, for every identity morphism, every object in your category. So if it's a group, you just have a single vertex, but if you have a category, you have more. And then in degree n, I suppose the n-1 I probably start with 0, shouldn't it? Let me think. No, I think I'm right. In degree n, the n tuples of morphisms whose composite is well defined, those are your simplices. They may be degenerate or not degenerate. And then there are, we won't worry too much about them, but there is composition at object xi, which gives you a face map, a boundary map from the n simplices to the n-1 simplices. And there's insertion of an identity morphism, which goes up to give you a degeneracy. So you can create simplicial sets mathematically in ways other than just converting simplicial complexes. They're handy objects. And no. It's not a simple. It's as in a simplicial set. It's the image of a. In the lecture yesterday, the sphere is a simplicial set with a single vertex and a single triangle. But what triangle has a single vertex? So it's the generalization. So I'm using degenerate.
In terms of the symmetry of simplex. You could just
Oh, they are. Yeah. No, they are simplices, I think. So you take your group, take two elements, and I'm going to think of them as being arrows because they're in my category, starting and ending, and take another one. Well, I suppose I'm going to have the composite as well. That's a triangle. Take three. So in that sense, it's a degenerate. They could be degenerate and so on. Theorem, old theorem, classical theorem. If G happens to be a group, and it's not true for a monoid, but if G is a group, these simplicial sets, you can talk of their homotopy groups if you want to, because they represent spaces. So, and if G is a group, then you can construct its nerve, which I'm going to think of as a simplicial set or as a space. I can talk of its nth homotopy group, and what the classical theorem is that the first homotopy group is isomorphic to the group G, and all other, it's connected, and all other homotopy groups are trivial. So I was talking about a BG yesterday, the classifying space of a group. If you didn't care about size, this would do for your classifying space. But it's very big. It is big. I think I have an example. Oh, no, in a moment. Yeah, okay. So you could, when I write NG for a group, you can think of it as BG if you want. And so that's the definition of the homology of a group. And then, well, I call, and I guess that's standard terminology, if you take the chain complex of this simplicial set, so now I've fudged things. I talked about the chain complex of regular CW complexes. You have to work a little bit harder to extend that definition to arbitrary CW complexes, and then this makes sense. But there's a chain complex which you can write down explicitly, and I'll call that chain complex the bar complex. And so what you could do, I've done it already, so I don't have to reproduce this. You could be naive and take your quaternion group again of size 8, and you could create this bar complex, and then take its homology, and you'd find the homology of the group. But it's pretty clear that in degree n, the bar complex is a free abelian group with generators, with the number of generators 8 to the power n. So there's an awful lot of generators. And so if, for example, in HAP, you did the first two commands, you'd have a chain complex, and then you could naively go and ask for homology of B. You'd be waiting a long time. So I tried this in Sage, and of course, you wait a long time. In fact, I didn't wait for Sage to finish. But if you use contractions and discrete vector fields to make things small, it becomes doable. And a couple of more commands show that in the first case, the ranks of the free abelian groups in the bar complex are shown there, whereas if you collapse things down, it becomes very small. So this is why collapsing can be useful if you're lucky.
What's the 6 indicate?
I only calculated 6 terms, so the it goes on forever.
It gets larger and larger.
Yeah, it's of size 8 to the power n. The number of generators is 8 to the power n, and so the matrices are rather big. So I just here constructed the first 6 degrees.
And the dimensions are always powers of 7. Is that?
Yeah. So they're powers of 7. I was caught out by that once because somebody showed me how their program would work, and they used the group of order 2. And it was thrown on me that I was thinking of 2 to the n. I thought, gosh, that's a fantastic problem. But you can actually normalize things and remove an identity. So, of course, 2 minus 1 is 1. 1 to the n is quite handleable. Whereas if you take a group of size 3,
The n minus 1.
which grows, yeah. So that's through me. But so the
Divide by 7 to the n in each place.
yeah. So I should. Well, I've fudged things there. In the implementation, I've constructed the normalized bar complex, making this minor saving in space. But yeah. Okay, so that's for groups. So what else can you say? From small categories. You can observe the following. If G is an abelian group, then the nerve is actually a simplicial group. If you go back here to the nerve, if you think about this categorically in terms of pullbacks and so on, it's kind of clear that if G is abelian, then these homomorphisms are actually group homomorphisms. So what you end up with is not just a simplicial set here, but if G is an abelian group, you end up with a simplicial set in which all of these direct products of are groups, and the homomorphisms are group homomorphisms. So you end up with a simplicial group, actually a simplicial abelian group. Everything is abelian, but yeah. That's just the observation. So, well, let me ask a question. Well, this is the answer. So let me ask the question first. In general, if you take a group and take its nerve, you won't end up with something which is a simplicial group. You'll just have a simplicial set. But simplicial groups are handy, especially if you're using gap, because gap is handy. For example, I know how to represent an infinite group. The infinite cyclic group, I can use Bettina's package and I can represent it in gap. The set of integers, or the infinite set, is harder for me to. So groups have that nice feature. So the question is, how can you generalize this observation? And you can do the following. You can define something, a condition on a small category. So G is a small category now, or a category. You can define a condition. Let's call the condition cat group. I have to say what that is. And the condition should be defined so that if G is a cat group, if the small category G is a cat group, then the nerve is actually a simplicial group. And also we'd like that the homotopic groups of the nerve as a simplicial group are trivial everywhere, well, except in degree 1 and 2. So if we could define cat group, we'd be able to kind of talk about simplicial sets or spaces with 2 non-trivial homotopic groups. So cohomology of groups is all about, from a topological point of view, cohomology of spaces with just a fundamental group and all other groups are trivial. But you could play the game, why don't you take a space with 2 non-trivial homotopic groups, and everything else trivial, and try to calculate homology there. And that's
G is going to be a category now.
G is going to be a category. I'm going to tell you, yeah, so throughout this, G is a category. I illustrated it for the case of a monoid or for a group, but in general, I have to give a condition on a small category.
So cat group is a category, and not a group.
So let me give the definition then. You can, let me answer it with a definition. I'll sidetrack. Okay, so Jean-Louis Laudet many years ago introduced something which he called a cat group, or a cat one group, because there are higher dimensional versions. And he gave a talk in the university in Bangor when I was a student, and in the audience there was Saunders MacLean. And as soon as Jean-Louis Laudet mentioned a cat group, Saunders MacLean stood up, hit the table. You cannot use that word. But there's no Saunders MacLean here, so I'm going to... Well, I don't know, maybe. So I'm going to use this word. Okay, so.
Is it something like a group object in the category of...
That's exactly... I'm going to... There we go. I beat you to it. Yeah, that was the... So a cat group then, or a cat one group in the Laudet language, or the official language is so a group is what? It's a set with a multiplication and so on, but you can define all of that categorically in the category of sets, but you can replace sets by any category with pullbacks and so on. And so it's a group object internal to the category of small categories. Because we want to, whatever. Yeah. With a mono. No. Well, hang on. No. All it is, forget them. Yeah. Okay, this is my easier definition. Okay, suppose G is a category. Yep. G has objects and arrows. Well, morphisms maybe. So G has a set of objects, and it has a set of arrows or morphisms, and it's a category. So every arrow had better have a source, which is an object. And every arrow had better have a target, which is an object, because morphisms have sources and targets. And okay, it's a category, so the category has a composition. What does category composition do? It takes two arrows and composes them, provided they're composable. So if you take two arrows which are not composable, you can't compose them. So what does it mean? I suppose you need the source of one to be equal to the target of the other. And so that's what this means.
S and T have to somehow...
Yeah, the source and the target, they have to be just group homomorphisms. And then you're taking this pullback. So this is the set of pairs such that S of the first equals the target of the second, or vice versa, whichever way you...
How is the morphism of a category a group?
It isn't. Whoa. No. Yeah. So it's a category, but now I'm working in the category of groups. So what I mean is, I need a set here which is actually a group. And I need a set here which is actually a group. And I need two group homomorphisms. That's the data structure. Yep.
You have a category that's enriched.
That's another way of putting it. I mean, that's another way. No, enriched means... No, enriched means something different. Enriched is a... Let me say it my way. No, I'm going to say it my way. What do I mean by a cat group? I mean a group which I'm going to call morphisms of G. I just mean a group. And I mean a group which I'm going to call objects of G. And I also will insist that I have two group homomorphisms which I'm going to call S and T. And these group homomorphisms have to satisfy the fact that I can certainly construct this pullback, and I'm requiring that G is a category. So there's a category composition. There has to be a way of composing arrows. And the composition must actually be a group homomorphism. And that is the definition of a cat group. And it turns out that if G is a cat group, the nerve is actually a simplicial group with this condition.
Would it make sense to, I don't know exactly what it means internal to the category groups, but could we take the abelian group?
Yeah, you can take any, so let me make it simple. What is your favorite category?
Let's say abelian groups.
Abelian groups. So then all I mean is the more G is an abelian group, ob G is an abelian group.
No, hang on. G is a category of internal. So G is the category of abelian groups.
No. If your favorite I mean, if usually we work with sets and everything is a set. Just live in a world where every set is a group. And every time you have a function between sets, it's actually a homomorphism. And everything you do for sets, you do in that world. And then define a category. And that is what I mean by a cat group. So a cat group consists of... Yeah, I have examples. I have examples coming up. I doubt it, but anyway, I have. Oh dear me, what's happening? I'm getting reaction, but it's the wrong kind of reaction. We can come back to this if anybody has a. Oh God, what do I mean by the? What do I mean by the classify? The classify. I wish I hadn't done this now. What do I mean by the classify?
Just the true object category.
Let me give you an example. Let me give you an example of what I'm talking about. I do have a it's not a great example, but it is an example. It is an example. Suppose that you like abelian groups. So let's suppose that A is your favorite abelian group. Doesn't matter. Yep, that's it. Yep. Yep. Now I have a favorite abelian group. I do. It's the trivial group. Now, there are two homomorphisms. They probably are the same, but there are two homomorphisms. And that is a cat group.
So A is an object, 0 is an
object, and the arrows are morphisms in whatever category you're working in.
The objects have to be a category.
Yes, so you need. No. The bit about the category is this. You start with this A over there and 0 there. Now you have to define a category, because a category, I mean, what's a group? A group isn't a set. A group is a set with a composition. A category is something with a composition. So you need also to have a composition in the picture. And that composition in this setup has actually to be a group homomorphism. Is that clear?
So what's the objects in this?
The objects is just one object. In the example over there, there's a single object, and every element in your abelian group is an arrow.
It's certainly not useful, this notion on a single object.
No, but
Is that not 2 or something?
No. Let me, I have one example. I have an example later in the slides which will help. Yeah, okay. The classifying space of a simplicial group now. So suppose you've got a simplicial group. Is a simplicial set. I haven't told you what it is, but if you've got a simplicial group by the classifying space I say the classifying space. It's a simplicial set which we denote by W bar of G. It's a simplicial set. And if G is a simplicial group, then it's also a simplicial set. So you can talk of homotopy. And G has to be the loops. We won't worry too much about this. I'm going to tell you what omega or W bar is in a moment. But G has to be homotopic to the loops on this simplicial set. But I'm going to let me just move on. For an abelian group A, your favorite abelian group A, when I define this W bar, we'll actually end up with a simplicial set, which is a space or a simplicial set which has second homotopy group equal to A, and all other homotopy groups trivial. So in general, you call such a space an Eilenberg-MacLane space, or maybe if it's minimal. And so this up in the cloud is the definition, I suppose, of what I'm going to call an Eilenberg-MacLane space. It's a simplicial set whose homotopy groups are trivial in every degree except for your favorite chosen degree k. Yeah? And I'm just stating that, you know, there's a result that says that for an abelian group A, this W bar will give us that.
Is it denoted K because of relation with K theory?
No, it is no. It's a K pi 1. I don't know where that comes from. A K pi 1 classif.
Maybe from the K may be also from class. I think K theory also comes from K class.
But-
From the German class.
Yeah, I'm not sure where the K. Yeah. I don't. You could also call it B. Well, no, you couldn't. Okay. Sorry.
Often you would just use a B for the N or for the W bar.
I'm gonna. I'm gonna.
Yeah, BG.
BG.
Yeah, you could also write BG there and then.
Let me just move on a minute. So, in fact, if A is abelian, then when I tell you what W bar is, I haven't told you what W bar is, but it will actually be a simplicial group. It'll be a simplicial abelian group. So you could go on and on and on. If I tell you what W bar is, you could take W bar of W bar. You know, W bar applies to a simplicial group. So if your output is a simplicial group, you can repeat. And W bar of the nerve will be a Ka3, a simplicial set with third homotopy group equal to A and all other homotopy groups trivial. So for a simplicial group G, the homology of G, we can define it to be the homology of the classifying space. But I will have to tell you about what the classifying space is. And if you take G to be a group, you can fit the homology of groups into this definition as well, but I'll say more about that in a moment. So I need to say, well, before I tell you what W bar is, let me just show that you can make calculations with all of this. So I don't know why, but if you happen to want to know what is the 15th homology of a space which has third homotopy group equal to infinite cyclic, and all other homotopy groups, including the zero, its connected space, all other homotopy groups trivial, you could ask what's its 15 homology in degree 15, and it turns out that it's cyclic of order 7 times 6. 42. 42 is the answer. There we go. Thank you. Yeah. It's
What is 7 times 6?
sorry.
I don't understand because either you put 42 or 7 by 3 by 2, but
Right. So why do you combine 3 times 2 to 6 and not have and not combine it with 7?
Yeah, I don't know why. That's interesting. Now, why is that? Yeah, I don't know what I'm doing there. I'm using. I'm not going to blame.
Natural 7.
No, I don't know why that. Actually, I'm not sure why that. I don't know the answer as to what's going on in the background. So it's cyclic of order 42. I don't know why it prints it out as not 7 times 3 times 2. I'll have to look into the inner workings of what's going on there. Okay, so here's the example you wanted. You wanted an example. So let's take time. Down here. Now, you might like non-abelian groups. So you take your favorite finite group even, your favorite group Q.
Let's take the one that Bettina gave us, the infinite diagonal group.
Any group, because I'm not going to work, I mean, I have to, the answers are complicated. So any group, really. Q is a group. Could be the quaternion group of order, anything. It can be anything. It's a group. And what you can certainly do is you can talk of an evening gap compute, well, if it's small or whatever, it's automorphism group. Yep. So you've got 2 groups. And then you have inner automorphisms. So an element of Q goes to the inner automorphism, which sends whatever an element Y goes to X inverse Y X, conjugates. Yeah, Y to the X if you want that. Y to the X, one way or the other. Yep. So for any group Q, you can certainly construct this group homomorphism. And this does relate to K theory, because where I came across this was working with Jean-Louis Laudet, who was interested in relative K theory and the Steinberg module and so on. So that's where I learned about it, but it's group theory. Okay, so now I think I've explained everything here. For an arbitrary group, you can certainly construct two group homomorphisms, S and T, I hope, as shown there. So alpha is an automorphism, X is an element of Q, and you construct two homomorphisms. So you can check that it's and also you can construct a partial composition. You can take the pullback over S and T of this semi-direct product. You take a semi-direct product, and you can take the pullback over S and T and get a very big group. But it's a general construction. And then you can actually define, and you can, if you're bored, you can check that this, I hope if I got it right, actually is a category composition. That it's defined whenever the source of one arrow equals the target of the other, that it's associative and so on. So this is an example of a cat group. It's a category.
So the elements of, so the automorphisms are the objects.
No. Yes. In the
Automorphisms are the objects.
The automorphisms are the objects, and the arrows are everything in this semi-direct product.
Yes.
Yeah.
And then you know from where to where the arrows go by
Yeah.
T.
S and T.
And
You compose using this.
yes.
So given a finite group, you can construct a cat group. And sure, if we knew what W bar was, it's time to stop, is it? Shall I just go quickly? And yeah, because I realized that I wasn't quite expecting but yeah, okay. So you can construct them. Now let me, well, I don't need to, I won't go through this, but I mean, you can take, for example, I took the dihedral group. These are some functions that are in gap. You can ask for this cat1 group that I just explained. I've given it the name automorphism group as cat1 group. I should actually say that this was implemented by a PhD student, Luan, who has implemented all of this. So given a finite group, or even an infinite polycyclic group or something, you can construct this cat group. And you can ask for this. By the size, I just mean the number of arrows in it. Yeah, so there's a lot of arrows in it. And this the next commands don't make sense. Well, they do. Sorry, the last command makes sense. Let me just go back. What am I talking about? If I have a cat group, so it does make sense, but I've missed something. If I have a cat group, its nerve is a simplicial group. Yep. So if I have a cat group, and I have one, its nerve is a simplicial group, and I define the homology of the cat group as the homology of the classifying space of the nerve. Yeah? So I've described a cat group, and I'm saying you can take its nerve. It's a category, so you can take its nerve, and you get a simplicial group. And then you can define the homology of that simplicial group to be the homology of this yoke W bar of G, which I haven't described. And there you get a definition. And so you can, for example, ask what's the homology of this cat group, except the cat group was large, So believe it or not, you can use homotopy. It gets a bit more complicated, contractions and so on, to produce a homotopy equivalent simplicial group, which is easy to work with, and you find that its homology is very uninteresting. It's so many direct sum of so many C2s with a C18. But let me go on and very quickly, and I won't go on too long, but tell you what the nerve is. Did I start 5 minutes late, or I can't? Yeah, I did. Okay, because it would be a pity to. Okay, let me tell you the nerve construction of a cat group, which should have come before that. So let's recall then that if you have a category, the nerve is a simplicial set, and in degree n, dimension n, it's all n tuples of composable morphisms. So those are your simplices. Now, if you start out with a cat group, I gave the theorem that the nerve is actually a group. That was a thing. I didn't prove it. I mean, I just stated that you can show that the nerve is a group. So since the nerve is a group, every term in the nerve is a group. So sure, why don't we form the nerve of each term? Each term is a group, so you can take the nerve. You take the nerve of the nerve, and you get what's called a bisimplicial set, which is, well. Anyway, the simplicial set that I'm trying to explain to you what it is, I haven't done that yet. W bar is my goal. So G is a cat group. And I want to tell you what W bar is. Well, it's going to be a simplicial set. Yeah? And we'll see that in degree n, this simplicial set will have as basis one basis element for every element in this term, which is got from taking the nerve of the nerve. So even if G is of size 8, this is big. And if G is infinite cyclic, well, this is infinite. So, we are faced with working with chain complexes, with infinitely generated free abelian chain complexes. Yeah. Yeah, no, Cn is, so what I'm saying is, I have yet to explain what W bar is, but it will be a simplicial set, which I'm going to call X. And I'm thinking of simplicial sets as being the same as spaces. Yeah, and I've kind of fudged, but I've kind of said that to a space you've got the cellular chain complex, and that's what this would be. But I still haven't said what W bar is. I don't think it's too difficult to tell you what W bar is. W bar is going to be a sequence of, I've said this already, homomorphisms. No, the chain complex associated to W bar is going to be a chain complex of free abelian groups generated by these rather large sets. How do you define the morphisms in the chain complex? Well, you actually end up getting a bicomplex in the first place. So if you look at, say, the bottom column, if you look at the right-hand column is just got from, I take the nerve of the group N0G. And then I take its chain complex, and I get a chain complex there. And then the second column, I take the nerve of N1G, get a chain complex, and I get a bicomplex, but a rather large one. And the chain complex we want is the total complex of this bicomplex. So that's what we want to calculate, and we want to calculate the homology of that. That's the goal. Yeah. So we want the homology of the total complex of this bicomplex. But the problem is that we're doing it on a computer, and these things are, well, if G is infinite, they're very infinite, super infinite. So the trick is, and I'll speed up very quickly now. The trick is to replace each column here is actually the bar complex. If you look at it, each column is just the bar complex, which is very big. So wouldn't it be better to replace each column by something which is homotopy equivalent, a chain complex which is smaller, but homotopy equivalent? And that's what goes on here. But here we have a bicomplex because things are functorial. When you mess things up by doing homotopies and so on, you no longer preserve functoriality, so you don't get a bicomplex. What you end up with is a filtered chain complex. I mean, the time is late, so I'm going to have to go quickly. But you end up with a filtered chain complex. But at least the columns and the terms in it can be rather small, because we know how to construct resolutions for groups and modules and so on. And then this is the bit that I need to get across, because how does it all work in GAP? So this is the glue. I mean, this is the point of the interpreting this. Let's define a homotopy equivalence data to consist of a chain complex R, a chain complex B, and a chain homotopy equivalence I, and an inverse, I've got it P. And I should be a chain homotopy equivalent. So H is this chain homotopy. So I need this chain homotopy. And that's what you define to be a homotopy equivalence. And then a perturbation on that is a degree -1 map on B. B stands for big, and R stands for reduced or kind of small. So B is big, and a perturbation is a degree -1 map on the big chain complex B, such that the square of D plus the perturbation is 0. Yeah, so this should be a chain complex. And then the theorem, which it goes back to various people. I cite Brown because Ronald Brown was my PhD supervisor, but there were other people at the time. And the description of the lemma that I've taken is due to Kranick more recently. So the description is slicker than in the original papers, is this. If the following exists, if you can, so you can think of this formally as being kind of series, and if you can take the inverse of this, in some sense, if that exists, if this condition exists, then you get a homotopy equivalence, chain homotopy, between the perturbed big chain complex and some perturbation of the small one. So just to summarize, you start off with a small and a big chain complex and a perturbation on the big chain complex, and all the theorem says is you can transfer, under suitable hypothesis, you can transfer the perturbation to the small. And not only that, you can read off by formulae homotopies and everything, on the small. So for the last slide, I think it is, let's just look at what's happening here then in the case in question. We have, I just go back. We want to calculate the homology of the total complex of that. So the game is you perturb and you'd end up with this, but gosh, what are the differentials? You have to construct the differentials. So let's have a look. We'll start off with an easy situation where the columns are precisely the bar complex. That's no problem. Oh, no, sorry, the columns are, the bar complex, the black columns. And for the horizontal maps, let me just take the 0 map everywhere, just to start off with. And then if I can certainly, up to homotopy, I can replace everything by smaller resolutions and still have zeros, and I still end up with a bicomplex. So I have a bicomplex there. So B, I suppose, is the total complex of this. R is the total complex of this. And I want to calculate, well, it's not this B I want. I want to perturb B, because the horizontal map shouldn't be 0. They should be something else. So I'll perturb, I'll get rid of the zeros. I'll say it was originally 0, the D, it was a 0. I'll perturb it to make it correct. And then the perturbation lemma, the homological perturbation lemma says you can transfer everything down to here to tell you what these differentials are. You can do all of that on a computer, provided that you have contracting homotopies on all the columns. And moreover, if you have a contracting homotopy on the row here, you can actually get a contracting homotopy, I've overstepped the mark. You need contracting homotopies on the columns. No, let me, that was wrong what I said. Let me rephrase it. We have contracting homotopies on these resolutions. And now I take a tensor with Z, so this is no longer exact, so I certainly don't have a contracting homotopy on the columns, but I do have the kind of the image of the contracting homotopy. And that image can be used to do all of the lifting and implement this perturbation lemma. And that's what's kind of implemented in that slide. Apologies, I think I had too much there. And tomorrow is something very finite and modular forms and unrelated to this. So. But yeah, I should stop there because I've gone over time. Sorry.